Go.
So the theorem that I'm going to introduce to you today is called the Konig-Egevary theorem. So first, before introducing the theorem, I'm just going to introduce a few notions. So suppose M is a M times N 0, 1 matrix, which means that all its entries are either 0 or 1. Then we define the line of M as its row or column. And we define something called a partial transversal, which is selection of ones from M such that no two are on the same line. So for example, if we have a 0, 1 matrix like this, so then if we select this one, and we select this one, then this one cannot be selected since it's on the same line as the second selected one. So this is a partial transversal of this matrix M. And the term rank of M is defined as the maximum size of the partial transversal of M. And the cover of M is the set of lines containing all ones of M. So taking this same example, we say that these two columns form a cover for M since it contains all the ones. Then we're gonna see a relation between the term rank and the cover. So suppose we have a matrix like this, and now let's first find the term rank of M. Term rank, which, as I want to remind you, is the maximum size of partial transversal. So we can easily see that the maximum size of the partial transversal is 3. This is one possible way of doing it. Now, if we want to find the minimum cover, so minimum cover is defined as the set of lines containing all ones of M with minimum size. And the minimum cover for this matrix is actually 3. This is one possible way of covering these. Now, notice that the term rank of M is 3, and the maximum size of the cover of M is also 3. Which these two are the same. So this theorem, this Konig-Egevary theorem, states that for any 0, 1 matrix, term rank is equal to the minimum size of cover. Yeah, done. Now, all right. Now that I've introduced Konig-Egevary, I'm going to try to introduce this theorem from the previous one. So I'm going to start with an example. Suppose we have a bipartite graph, a simple, finite bipartite graph as follows. V1, V2, U1, U2, like this. And then it's connected as follows. This graph is bipartite. This is trivial. Then we can construct an adjacency matrix as follows: Mg. Where this adjacency matrix is defined as follows. Then we can see that from this graph, we can see that maximum matching can be found as follows. This yellow one is the maximum matching of G. And this maximum matching can be related to this adjacency matrix by choosing the corresponding edges, which are this one and this one. But this maximum matching is also can be interpreted in this matrix as the partial transversal. Maximum partial transversal. Now, if we try to find the vertex cover for this graph G, we can easily see that the minimum vertex cover is as follows, this blue one. But this minimum vertex cover can be related to this by choosing the corresponding lines, which are these two. So this corresponds to the minimum cover. And we know that from Konig-Egevary that these two have the same size, which means that we can also deduce that these two have the same size. And we have the following theorem, which states that maximum matching has the same size as the minimum vertex. And this is the Konig Spring. Yeah, done. So this theorem that I'm going to introduce is called the Dilworth theorem. So before actually explaining the theorem itself, I'm just going to start with an example. So suppose we have a partially ordered set P given by, the Hess diagram is given as follows, which has a size of 8. Then we can construct a adjacency matrix as follows. So if I is related to J as following, then it has an entry of 1, otherwise it has an entry of 0. So and I have constructed the matrix as following. So because I couldn't write every number, these dots means that it has an entry of 1, otherwise all the other entries have an entry of 0. Now, to relate this partially ordered set and this matrix, we notice the following. We observe that if we have a chain of size k, then it corresponds to a partial transversal in that adjacency matrix of size k minus 1. PT is abbreviation for partial transversal. Now, suppose that we partition P into L chains. So if you see here, if we partition P into L chains of size K1, K2, and O, and so on, then we know that K1 plus K2 plus KL has to be equal to N, since P is partitioned into L chains. But we know that each chain has a corresponding partial transversal of size K minus 1 from this relation, which means that the total number of partial transversal is given as follows. But we know from this that all of this add up to 1, which means that we have a partial transversal of size n minus L. To show this a bit more clearly, let's take an example from the first example that I gave you. So suppose we decompose this into the following 4 chains. 1, 2, 3, and 4. Each chain, so notice that this chain has size of 2, this chain has size of 3, 2, and 1. This chain corresponds to partial transversal of size 1, 1, 5, which corresponds to this entry. This chain corresponds to a partial transversal of size 2, 2, 7, and 7, 8. So that one is going to be 2, 7, and 7, 8. This chain corresponds to a partial transversal of size 1, 3, 6. That's given by here. Right? And notice that all of these independent partial transversal, if you union these, then we still have a partial transversal, which in turn is the total partial transversal for this whole matrix, corresponding to the following chain decomposition, which explains this statement. Partition of P into L chains corresponds to partial transversal of size n minus L. Now, if we take M to be the minimal such that P can be partitioned into M chains, then we have that the term rank of M is n minus m by the definition of term rank, which was the maximum size of the partial transversal. Then, by Konig-Egevary theorem, we know that there is a corresponding cover of M by n minus m lines. Right? That means that we have M elements that are not used. And this M corresponds to the anti-chain of size m. So if you see in this example again, we have a term rank of 4, as you can see from this partial transversal, and this corresponds to these chains, right? And the unused ones are 1, 2, 3, and 4, which corresponds to a anti-chain. So now from this observation, we can state the Dilworth theorem. And the Dilworth theorem states that given a partial order set P, this can be decomposed into at least chains. Alpha P chains. Well, alpha P is the maximum size of an anti-chain of P. And this is called the Dilworth theorem. And your textbook asks you to prove it at probably chapter 2.6. This was the last exercise. So it will be a good exercise to try proving it on your own.
Okay, thanks.
Alright, so what we have done so far is that we started from this Konig-Egevary, and we have proved kind of the related theorems, which was the Konig theorem and the Dilworth theorem. But because of the lack of time, we could only prove these 3 theorems. There are other logical equivalent theorems, such as the Hall's-Merritt theorem, or the Birkhoff-von-Neumann theorem, Wenger theorem, or the Maxwell-Minkowski theorem. And these 7 theorems are one of the cornerstones in the field of extremal combinatorics. And you can try proving these. So these arrows means that, for example, this arrow means that Konig-Egevary can be proved using Maxwell-Minkowski theorem and so on. So please refer to the lecture note if you're interested in any other proofs or any other theorems. Thank you.